Hello, my name is Aniket Bose. In week 7 lab, we were introduced to 7 segment displays, how they work and how to use them. Now in today's lab, we are going to count the numbers using counters. Let's get into that. So here you can see I have this circuit. This is the wicket lab. This portion is the portion that controls these two 7 segment displays. So all of this circuit we discussed in week 7 lab, and this portion is the same as of week 4. So in week 4 we used LEDs to count the numbers using counters. Here we are just taking the counter output and using this control circuit to show the numbers on the 7 segment displays. Now what I have done here, this is the comparator IC. So here this pin is the VCC. So let's check the pin out. So here you can see this first pin, the 16 pin number 16 is VCC and the 15 pin is A3. First let's check the what is the B input. So the B0 is at pin number 9. So let's check that. So this is B0. This is pin number 9. This is connected to 5 volts. That means logic high. So B0 is 1. Then B1, which is at pin number 11. So let's check that. So this is the pin number 11. Here we have connected B1 to 0 volts. That is logic 0. And then B2 is at pin number 14. So this is the pin number 14. This is B2 connected to 0 volts. So that is logic 0. And then B3 here, it is connected to 5 volts. That is logic high. So the B3, B2, B1, B0 inputs are 1, 0, 0, 1. That means 9. Now what I am trying to do is I am using so you can see this brown wire. So let's check the pin out for that. This was the pin number 1, 2, 3, 4, 5. So let's pin number 5. What is that? So 1, 2, 3, 4, 5 is A greater than B out. So in A we have the output of the counter, and in B we have 9. And what I am doing is I am checking if A is greater than B out. That is, if the counter, whatever the output of the counter in A is it greater than 9 or not? So this brown wire will be logic high when A is greater than B out. And this is connected to a adder. So the adder pins corresponding to B2 and B1 is connected through this A greater than B out. That means whenever the counter value is greater than 9, these two pins, that is B1 and B2, that is 2 to the power 1 plus 2 to the power 2, that is 4 plus 2 will be 6, and this adder will add 6 to whatever the number in counter is, and then this adder is going to send that number after adding 6 to this segment display, and by doing that we are going to see the proper values in the ones place. For the tens place, I have used this BJT with A greater than. So here you can see there are two resistors. So these two resistors are driving this base. So this resistor is connected to A less than B out, and this is connected to A equal to B out. So whenever the counter output is lesser than 9 or equal to 9, this base is going to be high, and that will pull this collector low. In effect, this collector, which is connected to these 4 segments, first, second, third and fourth, so these 4 segments will get turned off because the collector is going to be pulled to the ground because this base was pulled high. So this way we are going to show the numbers. Now what I have done, I have used 2 buttons to step through the counting. We can also use ADLM to generate a square wave. So I am going to do both of them. So first I am going to do the experiment with this button. So let's check that. And one more thing, I have also taken into account counting downwards also. So there is logic for the down counting is there. I have used a quad 2x1 selector and the RCO pin. Whenever the RCO goes 0 to 1, I negate the value to make it go from 1 to 0, which loads 1 inside the counter, and then we negate it to get the proper down counting. And also for the clock of the second counter, so I have used 2 counters here and a selector to do the down counting logic. So one of the counter is used as a flip-flop for the down counting purpose. Using the RCO of the counter, which actually counts upwards, we control the 0th bit to make the number go downwards. So I have this LED and this LED. So this LED will glow when the second counter's 0th bit, that is B0, will turn on, and this LED will turn on when the RCO goes 0 to 1. So let's check the circuit. So here I have the ADLM. So let me power it up. So I powered the ADLM. Now also one more thing, I have the channel B is measuring our button output. We have here a debound circuit. So this button output is going to a Schmitt trigger, and we are taking the negated waveform to use as a clock for the first counter. So let's check the waveform of our push button. So let me run the circuit. So now if I press this button, you can see I have pressed the button and the waveform goes to 0 volts, and when I release the button it goes to 5 volts. Again I press the button, the waveform goes to 0 volts and then comes back to 5 volts. So this way I am stepping through the, so I am generating the square wave using this push button. And one more thing also, here when I push the button, then the counter counts up, and when I release the button, it doesn't do anything. Then I again push, the counter counts up, release, it doesn't do anything. With the second button, what I have done, in the release it counts up, in the push it doesn't count. So we will also check the second push button. So this is the first push button. So let's step through the counting. So this is 7, then 8, then 9, then 1, 0, 10, 11, 12, 13, 14, 15. And now you can see this is the RCO bar, that is the negated of RCO. So we have used that as a load bar value for the second counter. And when this RCO goes from 0 to 1, this RCO bar goes from 1 to 0. In effect, that loads a value here to the next pulse. This bit, the 0th bit, will become 1. So let's through it again. So this will become 14 and it will glow up. So this becomes 14 and it glows up. Then it starts to down count. Then it reaches 0. Now it will again count up. So this is the way my circuit is working. And let's check the next push button now. So now if I use the output of this push button, so let's check what happens. If I now push the button, the counter will not count up, but when I release the button, it will count up. So I pushed it, it doesn't count. Now I release the button, it counts. So let's check the waveform also. When I press the button, it goes to 5 volts. When I release the button, it goes to 0 volts again. So this is the push button output. So we had seen the waveform of the push button, but we didn't see the actual clock, which is the negated value of the push button. So let's check that also. So this is the channel B. I'm going to connect it to the negated output. So let's check that waveform also. So now if I push the button, when I don't push the button, the value is 0 volts. The clock value is 0 volts. When I push the button, it goes to 1. When I release it, it goes to 0. When I push, it goes to 1, and release it, it goes to 0. So this is the clock. So that's why when I push the button, it goes to 5 volts and the counter counts up, because this is the rising edge. When I push the button, a rising edge occurs. That's why counter counts up on the push, and on the release it doesn't count. And now let's check the second push button. So I have connected it to the next push button, the clock value. So I have connected the second push button output to the Smith trigger. Now let's check the push button waveform. So when the button is not pressed, the value is 0 volts. When I press the button, it goes to 5 volts. On release, it goes to 0 volts. So the push button output is generating a positive edge on the press, and on the release a negative edge. And for the clock, because we have used a negated version of this, so on press we will get a negative edge, and on release we will get a positive edge. That's why for the second push button, on the release in the clock, in a positive edge comes and the counter counts up. So let's check that. So I am going to connect it, the channel B, to the negated value of the push button output. So you can see here, initially this is 5 volts when the button is released. So this is the actual clock. The actual clock is 5 volts when released. When I press it, it goes to 0 volts, and this is a negative edge. So the counter doesn't count. When I release the button, it will go from 0 to 1, creating a positive edge, and the counter will count up. Now let's take the ADLM square wave output as the clock. So I'm going to connect the channel A, and the channel A bar will be the actual clock, though that is the negated value of the channel A. So I'm going to generate a square waveform on channel A. So the shape is already selected to square. It will go from 0 to 5 volts with a frequency of 1 Hertz. So now if I run the circuit and through channel B, we are measuring the negated output. So here you can see this next yellow wire is the channel B. So let me change the channel B color. So I'm going to use this for the channel B. Channel B is measuring the actual clock, and channel A is the input waveform.